Okay. Thank you very much for the organizing committee. They made this organization exist, and thank you very much for all of you guys who joined this amazing organization. And lastly, thank you very much for the Doğa. She did an amazing job. Now she's going to talk about some basics of some classification and regression algorithms.
Hello everyone, my name is Doğa Seçkin, and today I'm going to be making a presentation about regression and classification. I will start by giving some introduction to the topic by setting up some definitions, and then we are going to take a look at our models, namely linear regression, logistic regression, KLinear neighbors, and decision trees. And for statistical learning, we need a data set. So let's define what a data set is. It consists of a set of tuples with elements called x's, which are the input values, and y's, which are the label values. But what we can think of these tuples as a function, namely a labeling function. And what does a learning algorithm do? It tries to mimic this function. It is also a function that tries to mimic this f. But how does it do that? It looks at the data set and assumes that our labeling function is a well-known function. And then it creates a training data set and the test data set from using our whole data set. And it uses the training data set to try to understand the relationship between the x's and y's. And it uses the test set in order to see how well it behaves, how accurate it is. And this is called supervised learning. There's also an unsupervised learning in which there are no training and test sets, and there are also no labels in the learning process, but we are not going to look at that today. All the models we are looking at today belong to supervised learning. But I said that the learning happens inside the training set. So it gets more and more accurate in the training set, right? But what about the test set? Sometimes it is not that accurate in the test set, even though it is very accurate in the training set. And this is called overfitting. This happens a lot, and we try to avoid this. And also, all the models we are looking at today are either classification or regression models. Classification is when our label set is discrete and finite. For example, it can be a set of blue dots and orange dots. And the regression is when the label set is real numbers. So it can be temperature, it can be weights of students in a classroom, anything that can be shown as a real function, a real set. Let's start with our first model of today, called linear regression. And the best way to understand it is to look at an example. This is a one-dimensional input case. So this is our input x values, and these are our y values, which are the real numbers. So this is a regression problem. And we want to use this on a data set where there is a linear correlation between x and y values. This is a good data set to use a linear regression model. And what we are trying to do is we try to find a best fit function that behaves well on these data sets. This is our training set. So we write a equation for a line, and we try to find the best beta 0 and beta 1. To better understand this, let's look at a two-input example, two-dimensional input example. These are the input values, and this is the label value. This can be like this first x1 can be the weights of the students in a classroom, x2 can be their heights, and y can be their strengths, so something correlated to that. And our equation is an equation of a plane, because now we are not fitting a line, but we are fitting a plane. And in higher dimensions, we get another linear function, which adds beta 3, x3, and so on. So we can represent our model with this vector function, and our beta is a vector now, and we try to find the best beta. But how do we do this? We need to define an error first. An error our error here is called a residual, and the residual is these vertical distances between the data points in the training set and the prediction made by the model. And we want these to be very small. How do we force them to be small though? We need to use an estimator to do this. And our estimator is called the residual sum of squares. It takes every single residual, it takes their squares and adds them up. And how do we force this to be small? We take a derivative with respect to beta, and when we solve it, we get this equation. Now when we multiply x with this beta, we get a prediction for our label value. We can use linear regression for classification problems as well, but that's not that much preferred. What we usually use for this type of a problem is called logistic regression. This is our second model of today. And our data set consists of a Bernoulli distribution, which gives you either y equals 1 or y equals 0, depending on some probability. If you use linear regression, you see this line, which is not a well fit. And what do the y values mean? You don't really have a very good sense of what y values mean. But in logistic regression, y values are between 0 and 1, and they give us the probability values of getting y equals 1. So let's start by looking at an example. I found a very interesting data set. This is the Space Shuttle Challenger that has a mechanical part called O-rings. These O-rings sometimes fail depending on the temperature. And this is a data set for temperature to these y values. And when the y values are 1, it means O-rings fail. And if it's 0, that means it doesn't fail. So how do we create that S-shaped function? So we use logistic regression, and logistic regression is something called a generalized linear model, because we have this linear part, but it's not equal to directly y, but it's equal to this function called a link function. These pi's are the probabilities. This inside part is called odds, and our link function is called log of odds. And if you do algebraic manipulations, you get this equation, this function for pi, the probabilities, and this gives us the characteristic S-shaped function of the logistic regression. But this S-shape can be a wider S and narrower S. It can be more of a Z than an S. So we need to find what type of S-shaped function it is, and in order to do this, we need to find alpha and beta values. So what we do, we need an estimator again. And our estimator for this model is called maximum likelihood estimator. So we need to define what a likelihood is. A likelihood is a joint probability of guessing every point on the training data correctly. We multiply these and get our likelihood function, and we want to maximize this. So we take a derivative with respect to alpha and beta and get two new equations. We have two equations and two unknowns, alpha and beta, so we can solve these for alpha and beta. And then when we plug them into the equation for pi, then we get this figure, this curve. So how do we read a logistic regression curve? Let's say we are given an x value, we go to its y value, and it gives us a probability for getting y equals 1. Well, this is much more better and useful than just getting y equals 1 or y equals 0 classification, because sometimes we might want to do something with the probability information we have. After all, a 99% and 51% are not the same thing, but usually they can be classified into the same thing. So knowing the probabilities is actually very useful for us. And our third model for today is called KLinear Neighbors, K nearest neighbors. And here we have a decision boundary. Every point above it is classified into one class, and everything on the other side is classified into the other class. And what this has as a strength is it has a very flexible shape of a decision boundary. If this was a linear regression, this would be just a line. But how do we choose where to classify which point. Let's say our k is equal to 15. So this is a 15 nearest neighbor classification. And let's choose a point on the domain, any point. It doesn't have any point in the test set. To classify it, we look at the nearest 15 points. And let's label oranges with y equals 1 and blues as y equals to 0. When we want to classify a point, we look at the nearest 15 points and take the arithmetic average of their labels. If it is above 0.5, we classify it into oranges. And if it is below, then we classify it into blues. But what if we change k? This is a 1 nearest neighbor classifier. As you can see, it classifies every point in the training set correctly. So the lower the k, the more accurate the prediction on the training data. But what if the test data? It can still perform very poorly in the test data. So this is why k-nearest neighbors method is very prone to overfitting. So we need to be very careful which k to choose, which is usually done by using a test set or cross-validation, but I'm not going to get into much detail of that. Brings us to our last model of the day. So if you're interested in Bitcoin mining, listen carefully. This is used a lot in that field, but be aware this is not an investment advice. So this is decision tree. Decision tree is both a classification and a regression model. And there are many different ways to build a decision tree. So we are going to consider one very famous example, which is called CART by Leo Bryan. So let's start with the classification tree at first. This is the classification data. So we want to classify every single point into either crosses or circles. And we put them into a diagram and call the first node, these are called nodes, first node of the diagram as root node. Then we make a partition. You can normally make a diagonal partition as well, but in CART, you need to do either horizontal or vertical partitions, and you need to partition only once in each step. So you create 2 new nodes in each step. How do we do the partition? We try to make as pure nodes as possible. What is a pure node? If we have a probability of getting a specific label very high and very low probability of getting the other label, then we call that node a pure node. So this got a little purer here. Then we keep on making new partitions. Here we partition the T3, so we need to split this T3 node, and we go on like that. But how do we decide where to split exactly? We need some definitions at first. Prior probability is probability of picking a class label, picking a data point with class label J from the distribution. This has nothing to do with the decision tree itself. It is just a property of the distribution. Then secondly, we have a probability of picking a data point in a specific node with a specific class label. And we define it like this. Then to find the probability of picking any data point in class label T with any label, it doesn't matter. We add them up. And then this is a very important probability. It's the conditional probability of picking a data point with a class label J, given that you're already only looking at a specific node T. And now we can actually give a definition, a quantifying definition for what a pure node is. And our function for this is called impurity function. Impurity function is a function with positive inputs, which add up to 1. And it also has these conditions. It should be positive. It is symmetric with respect to its input, so changing the inputs doesn't affect the result. And also, the maximum possible value is when all the inputs are equal to each other. We can already see that we can use probabilities for the inputs, right? So if in a node we have equal probability of picking any class label, then it's not a very pure node, right? This tells us that. And when is it the purest node possible? The minimum value is 0. And it is obtained when we have 100% chance of getting one specific label and 0% chance of getting any other labels. So it's the purest node. It's called a pure node. There are many different impurity functions, but two mainly used ones are entropy and Gini impurity, and CART uses Gini impurity. So I calculated the Gini impurities for the data set that we saw in the beginning of this section. In the root node, we had this many crosses and this many circles, and then we kept partitioning it. What do we expect? Firstly, you see here we have a completely pure node, right? So we expect its impurity function to be 0. What else? Here we have almost a pure node, almost completely pure, so it should be very close to 0. And the maximum possible value for Gini impurity is 0.5. So here, this node seems kind of a very impure node. We almost have the equal possibility of picking either one of them. So this should be very close to 0.5. Let's check. That's true. T5 equals 0. This is what we expected for a pure node. T2 is close to 0. And also T3 is actually very close to 0.5. So it fits our expectations. Now we define the impurity of a specific node. We can define an impurity change. An impurity change is the impurity of this node, for example, minus its child node's impurity. And we try to pick we consider every single split in each splitting, and we choose the one that maximizes the highest impurity change, that causes the biggest impurity decrease. And when the stopping condition is satisfied, we call that tree Tmax. And the stopping condition can be anything you want. It can be stopping until a certain number of splits. It can be stop when all the nodes are pure nodes. So after choosing that, the tree you get is Tmax. Now we need to label these nodes. Now we built the tree, we need to label these nodes. And to do that, we define a cost at first. It is a quantity relating to misclassifying a data point with label J as a data point with label I, and it is 0 if we are making the classification correctly. And then in order to do the labeling, we take a weighted sum of this with weights as probabilities, and the label which is misclassified the least amount is going to be our label. Also, we have a quantity, but when you put that label into the sum, the quantity you get is called misclassification cost of a node. And if you add them up for the leaf nodes and with the weights, you get the misclassification cost of the whole tree. This result is very important. It says that the splitting action either keeps the misclassification cost the same or decreases it. So you would think that, okay, then splitting as much as you can should be a good thing, right? Well, wrong, because that would cause overfitting. In order to avoid overfitting, we use an augmented cost function, which punishes the act of splitting itself. But we already built Tmax. How do we avoid overfitting now? We prune our tree. Pruning is defined like this. If you want to prune this tree from this branch, you remove all the data, all the nodes below this node. So you get this one. And we have another definition called optimally pruned subtree. This tree is the tree that minimizes our alpha. And also if you prune any more, then the tree, our alpha would change. Then it's called an optimally pruned subtree. Why do we need this? The math here is a little complicated and long, so I'm going to talk about the method. We take an optimally pruned subtree. Then we find the pruning that changes the alpha the least amount. And then after we find this, we prune the tree there and then keep pruning until our tree is optimally pruned. Then we take this alpha and the tree and put them into a set. Then we repeat until we get to the root node. So now we have a set of trees and a set of alphas. And we need to choose the one that fits our purposes the best. And in order to do that, we use the test set or cross-validation, which we are not going to get into the details today, but these are also very important to learn if you're curious. This is a resulting tree. And how do we do the classification? Let's say we have a point 3, 5. we start from the root node, and then we go to either x smaller than 5 or x bigger than 5. Our x is 3, so we go this way. Then we look at our y smaller than 8 or bigger than 8. Our y is 5, so we go this way. We keep following the correct ways and end up here. What is the label of this node? It is a cross. So we label our data point as a cross. And the last thing we are going to talk about is the regression trees. The regression trees are a regression problem. So we try to fit a function onto this data set. And to do that, we need the nodes and the labels. The labels are determined by taking the arithmetic average of the data points labels, the y values. And then when we split, we take the average for both sides and we split the tree. Then we keep doing this to get the resulting tree. It's very similar to the classification tree, so I will only talk about the differences. Labels for each function are determined by an arithmetic average, and the error is here the residual sum of squares, like the linear regression case. So this is our R, and the misclassification cost is again calculated like this. Rest is the same. You build the tree, you prune the tree, then you select your tree by using the same methods in the classification tree. So this ends our discussion in the regression tree. What I would like to say is this is very important. I couldn't get into details of these much, but these are the methods for avoiding overfitting. And the most widely used ones are bagging, random forest, and ADA boosting. So if you're curious, I would highly suggest reading about these two. And this concludes my presentation. I hope you enjoyed it. Thank you for listening.
Do you have any questions?